you very much.
Thank you, Bernard. Yep. So today I'll be talking about Bayesian Nonparametrics. But before I start, I'd like to thank a few people. Actually, I'll start off with thanking the Canadian High Commission for giving my passport back in time. And I've also like to thank, of course, many of the very smart people that I've worked with over the years, my students, postdocs, collaborators that I've kind of listed here. I hope I haven't missed anybody. And particularly, I'd like to thank Zubin Garamani, Peter Orbans, and Michael Jordan. Their kind of teachings and tutorials have influenced the way I'm presenting this work here. Particularly, Mike Jordan, I've actually been working on a gentle introduction to Bayesian Nonparametrics with him, and some of the ideas for how to present this topic in this first lecture today is kind of arose due to discussions with him. Okay, I'll start off with just a general introduction, recap of Bayesian machine learning. I think lots of people have talked about this already previously, like Zubin, right? So start with probabilistic machine learning. Okay, so machine learning is all about trying to learn from data, right? So how do we learn to process data? How do we learn representations of our data and learning some sort of higher order structure that's useful from data? Okay, and we all know that data is often kind of stochastic, it's often noisy, it's often chaotic and quite complex generative processes, and also at the same time, the generative processes are often also only noisily observed. We don't observe the whole thing. We don't observe everything about the world, but only some parts of it. And also it might be also partially observed as well, right? So there's lots of uncertainties that we have about our data, okay? There's lots of things that we don't know about it. And the idea of probabilistic modeling and probabilistic machine learning is that we should use the language of probability theory as a kind of a rich language to express these uncertainties. And this is very useful because this language of probability theory kind of gives us a way to reason in a coherent manner about all these uncertainties. Okay. So that's theoretically speaking, but also practically there's been a lot of tools that has been developed over the many years that helps us to deal with kind of modeling. How do we actually go about modeling and solving modeling problems using this language of probability theory, right? So the idea of using kind of graphical models to help us visualize complex models for complex problems. So there's also another idea in which you could kind of build more complex models from simpler parts by kind of basically piecing them together like a bit like Lego blocks, basically, right? I think you guys have probably seen this over the last 2 weeks. Some of these examples. Also, I think more recently, I think in machine learning, people have been developing a lot of very efficient computational tools to derive algorithmic solutions for inference in these models, right? And I think one of the important things with this idea of probabilistic modeling is that there's a separation of questions about modeling from questions about algorithms. Okay, so often when you have, say, a large-scale problem and you need to actually implement your inference algorithm on very efficiently over a cluster or something, then there's often approximations and heuristics that you have to make. But whenever you introduce approximations, it's often useful to think about, what is the ideal situation? If you could use all the computation that you have in the world, what would be the ideal situation ideal problem that you could solve? And those are problems that are kind of posed by kind of looking at the model itself without and separating it out from the algorithmic kind of approximations in a sense. Okay. I think that's a very useful way to think about this kind of this ideal situation. Okay. Right. So just to introduce, recap some of these ideas again. So let's say that our data consists of some data sets of n observations or items, x1 to xn, and maybe we might have some set of latent variables, okay, say y1 to yn. So each y is associated with the corresponding observation. So these are kind of variables that we may be interested in. Say x's are our observations and y's are the things that we may want to infer about. Okay, that's in the world. And maybe we might have a certain set of parameters, theta, okay? And a probabilistic model is basically a parameterized joint distribution over the variables that we're interested in. So we have a joint distribution over this set of 2n variables, x1, xn, y1 to yn, and they're going to be parameterized by theta. Okay? And we can typically think about this as a generative model. So we can think of this as basically the way our data may have been generated by the world. Okay? So we'll see some examples of this a bit later, I guess, just kind of very abstract examples, I guess. And the problem of inference is basically a problem of learning about the latent variables that we don't observe, that we care about, given some observed data. And this is given by the posterior distribution of the y's given the x's, which basically by Bayes' rule is given by that. Okay? So basically it's the joint divided by the marginal of the x's. Okay? Right, so here's a few just definitions of things, I guess. So the problem of learning is typically posed as a maximum likelihood problem. So this is a problem of not really learning about the latent variables themselves, but really learning about the parameters that describe the generative process. Okay? So what we are interested in is to find a theta that maximizes the probability of our observed data. Okay? So that's just learning. And a prediction is basically we would like to kind of predict or to compute the conditional distribution of some future unobserved data, okay, given our data set. Okay. And classification, of course, is if you have a certain number of classes, each class parameterizing some joint distribution, then we might want to find the class that gives kind of the highest probability to some future test item, okay, given the parameters that we have learned. Okay, okay. So there's lots of things that I guess you guys have learned over the last 2 weeks. Skip over that. So that's probabilistic modeling. What we'd like to do in Bayesian modeling is to take one step further. Okay, so in probabilistic modeling, we typically separate between two different problems. One is learning, which is to learn about the parameters that parameterize our generative distribution, and inference, which is to compute the posterior distribution over our latent variables, given the parameters that we have. Okay, so they are typically thought of as two different problems. In Bayesian modeling, instead of thinking of them as two different problems, we like to just kind of put them both under one umbrella and basically treat both inference and learning as basically the same problem. Okay. To do that, what we'd like to do is to first introduce a prior distribution over our parameters, which describes what we think are likely parameters that comes from our prior knowledge about the problem that we're trying to solve, okay, or the problem that we're trying to model. Okay. Then, so once we have a prior distribution, we can then write down the joint distribution over our observations, our latent variables, and our parameters as basically the prior times the conditional probability of the data and the latent variables. Okay, so that gives us the joint distribution over everything, and then both inference and learning can be thought of as trying to compute posterior distribution over both the parameters and the latent variables, that neither of which we observe, given the observed data set that we have here. Okay, and now the problem of prediction and classification can be formulated in the following way. Basically, prediction is simply to compute the conditional distribution of a new test point given our data set, where we marginalize over our latent variables and over our parameters too. Okay. Classification is to compute the conditional probability of a new test set given our current data set, which could be split into the different classes. Okay, so for each of the different classes, we may have a different subset of a data corresponding to that class, and so this is simply to compute the predictive distribution under that class. Okay. And then, of course, we like to find a C that maximizes this predictive distribution to classify this new test point. Okay. So just to give you two very simple abstract examples of probabilistic or Bayesian modeling. The first one is going to be model-based clustering. Okay. So this clustering problem is basically a problem of given a data set that may look something like that. What we like to do is to simply model this data as coming from a certain number of heterogeneous unknown sources. Each source maybe could basically lead to a different subpopulation of our data, which may have a different characteristics. Okay? So for example, in this case here, we might want to cluster our data set into maybe 3 different clusters, for example. Okay. Yeah, and typically, so this is called, the approach we're going to take is a model-based clustering. And what that means is that we're going to model each cluster using some parametric model. So for example, we might assume that for this particular problem, that each cluster corresponds to a Gaussian distribution over that subset of data with some mean and some covariance matrix. Okay. So it's going to be parameterized by a Gaussian in this case. So the generative model that we might pose to solve our clustering problem is the following. Okay. So we're going to assume that we have a Zi, which is going to indicate which population each data item belongs to. Okay, and Zi here is going to be latent, it's going to be unobserved. We don't actually know which population each observation belongs to, but we can assume that it does come from some population. Okay, and we're going to say that in our generative model, for every data item, the way it's going to be generated is in the following way. We're going to first pick which cluster it belongs to, according to some distribution over populations. So pi is going to be a vector of probabilities that sum to 1. Okay, so it's going to be what's called a mixing proportion. So pi is simply a vector of length k if we assume that there are k populations in our problem. And basically, pi k is simply going to be the probability that Zi takes on value k. Okay, and so first we're going to draw which population that data item belongs to. And then we're going to model the data item itself, xi, okay, given the population that it belongs to, as coming from some parameterized distribution, that's indexed by Zi. Okay. So for example, coming back to this case here, theta might correspond to the mean and the covariance matrix of the Gaussian, and F is simply a Gaussian with the corresponding mean and covariance matrix. And we're simply going to say that xi is going to be distributed according to a Gaussian with the corresponding mean and covariance, given the population that it belongs to, which is Zi. Okay. So this is the generative process. We're first going to pick the population that it belongs to, and then we're going to generate the data from the parametric model corresponding to that population. So we're going to take a Bayesian approach here. So what we need to do now is to also put a prior over the parameters of this model. Okay, so the parameters of this model consists of the mixing proportion pi and the parameters of each Gaussian. Okay, so for the mixing proportions, a typical prior that people use is a Dirichlet prior. Okay. And this is a typical prior because it's computationally very easy to work with. It's conjugate to multinomial sampling, which is what this first step does. Okay, and what that conjugacy basically means is that conditioned on everything else, the conditional distribution of pi is also going to be Dirichlet, so it's going to stay in the same family. Okay, so that all the computations become very easy. And then for each cluster K, we also need to introduce a prior over the parameters of that cluster. And let's say that that prior is just going to be some prior H. Okay, so we can place, for example, a Gaussian prior over the mean of each Gaussian, and maybe some inverse Wishart prior over the covariance matrix of the Gaussian. Okay. Okay, so here's a graphical model that expresses this joint distribution here. This part here is going to correspond to our data set consisting of n data items. And basically, this plate here, basically what it says is that we're going to independently and identically describe each data item by first generating xi and then generating zi and then generating xi. Okay. And over here we have our parameters. Zi depends on pi because of this dependence here. And then xi given zi and theta would depend on theta as well. And we have a plate here as well because what we're assuming is that the parameters of each cluster are going to be independent and identically distributed coming from H. And I'm going to place what's called the hyperparameters, alpha and H, onto this graphical model as well. Okay. So basically over here, the edges describe a dependence that we are going to assume. The absence of edges describe actually conditional independencies, while the little nodes here correspond to the random variables that is described by our model. Okay. So the problem here basically now is, given some observations of the axis, we would like to infer the latent variables and the parameters in our model. Okay. And basically, if you could compute the posterior distribution, then often that posterior distribution actually tells us something about the various populations that exist in our data, as well as the probability of each data item belonging to each population. Okay. So we can generalize this, for example, to hidden Markov models, right, where we're thinking of this as basically clustering over time. Okay. So our observations now are going to be a sequence x1 to x tau, okay, that we assume comes from some time series type of problem. So for example, speech recognition, or maybe mocaps of data, or videos of data. Okay. And we're going to assume that our observed data here is generated in the following way. We're going to have some sequence of latent variables, z1 to z tau, which is going to be a Markov, going to have a Markov structure. Okay. So that's what this chain here describes. And then conditioned on the latent variables z1 to z tau, each of the observations are going to be conditionally independent and depends only on the corresponding latent variable z. And this part here is going to be the parameters of the model. Pi k is simply going to be the transition probability given that the previous state is k. Okay, so given that z1 takes on value k, then the conditional distribution of z2 is going to be given by pi k. Okay, and then for each latent states k, we also have a parameter which describes, basically this is the emission, which describes the emission distribution given that the latent state belongs to states k. Okay. We may also introduce priors over the transition probabilities and over the emission parameters as well. Okay. Okay, so this is just a graphical model. So again, the arrows here basically describe dependencies that we're going to assume in our model, right? So we're going to assume that each latent variable z depends on the states of the previous latent variable, and each observation depends on the corresponding latent state. And these arrows here basically describe how these variables and the conditional dependencies are parameterized by our parameters. Okay. Okay. So here's another example: collaborative filtering. Okay. So here the data consists of actually an array now. Okay, it's an array here. So we think of this as so these are going to be the users of say a Netflix, and these are going to be the movies that Netflix provides. Okay, and the data consists of basically for each user I, the rating that the user gives to the corresponding movie J. Okay, so Rij is going to be whether the user likes the movie or not. Okay, so this gives us a two-dimensional array. And the way we might formulate this collaborative filtering problem is that we may observe a certain subset of these ratings, and what we'd like to do is to fill in all the unobserved ratings in this matrix. Okay. Right, so basically what we'd like to do is to predict how much each user likes each movie, okay, so that we can recommend movies that the user hasn't seen but maybe might like. Okay. And the way we're going to do this recommendation is basically by kind of modeling. Think of this as modeling each user as actually having a certain set of features. So maybe a user might like action movies, comedy, maybe I don't know, some French movies or something. Okay. So those are the features that describe the interests of the user. And we may also have a certain collection of features for each movie. So we might describe a movie as an action movie that is from France, for example. Okay, of course, we don't observe the user features, nor do we observe the product features. And we can model the rating that a user gives to a movie as basically some Gaussian with a mean given by a dot product between these two feature vectors, plus some noise, for example. Okay, so this is a very standard model that people have is very well explored. Okay. Right. So those are just simple examples to kind of give you some idea of what a probabilistic modeling is about. Okay. So I guess I forgot to mention that. So these are the unobserved things. The features are unobserved. We observe some collection of ratings here. And the problem of learning and inference is basically about learning about the unobserved features as well as predicting on ratings that we haven't observed yet. Okay, so we like to compute the posterior distribution over all the unobserved variables in our model. Okay, so all three models that I've described so far are what's called parametric models. Okay, so they are parametric in the sense that here's our model, and we have parameterized our model using some finite collection of parameters. Okay, and this is, of course, a very successful methodology. I mean, there's a huge literature and active community solving all sorts of real-world problems with this idea of a probabilistic modeling. Okay, but today what I'll be talking about is going to be Bayesian models as well, but it's going to be nonparametrics. Okay, so it's going to be. So the first question is, what is a nonparametric model? Okay, so when we think about parametric models, what we think about is it's going to be a joint distribution that's going to be parameterized by something, by some parameters, basically. That's why it's called parametric model, right? So what is a nonparametric model? It doesn't mean a model that doesn't have any parameters. Often, actually, it's the other way around. It's actually typically thought of as a model that has a really large number of parameters. In fact, typically an infinite number of parameters. So in that sense, it is not a parametric model, because typically we think of parametric models as having only a finite number of parameters. But if you have an infinite number of parameters, then it's no longer a parametric model. So it's just simply a really large parametric model. Okay, so here's one possible definition of what a nonparametric model is. Another way of defining what a nonparametric model might be is actually a parametric model, but actually where the number of parameters increases with the data. Okay. So the idea here is that if you start off by making a certain assumption that there's only a finite number of parameters, then as your data set grows, as you observe more and more data, then the amounts that you can learn from your data is going to be limited, because you start off by saying that this is all I can learn, is only this finite number of parameters. Okay, but typically what happens is actually the real world is often infinitely more complicated than any parametric model that we might be able to impose in modeling assumption. So what we like to do is to say that as our data set grows, we would like to be able to learn more and more about our world, which is kind of, in a sense, infinitely complicated. Okay, so to do that, we need a model whose number of parameters is actually increasing as our data set increases as well. Okay. So another third definition of what a non-parametric model is that it is a family of distributions that is, I'm just going to read this out, that's dense in some large space that's relevant to the problem at hand. So I'll actually come to that a bit later. So the idea here is that in many machine learning problems, there's often a space of objects that's kind of the natural space in which we could think about our problem. And often this space is infinite dimensional in size. Okay? And so a non-parametric model is basically a model that kind of can span this whole infinite dimensional space. Okay, I'll come to that a bit later. So the first, so that's what kind of different possible definitions of what a non-parametric model is. Yes?
Just to help visualize around this, could you give an example?
Of which one? All of this? Okay, so a simple an example that I think you guys probably have heard before is the Gaussian process, right? So maybe I could move to that actually. Move to that. Okay. Oops, sorry. Okay. So suppose that the problem that you are trying to address is a regression problem or classification problem, right? So in this problem, what we're interested in is we have some input space, and what we'd like to learn about is some function which maps inputs to outputs. Okay. So here's a function, and the points here are our data set. Okay. So in this case here, the space of objects that we are naturally interested in is actually the space of continuous functions from inputs to outputs. Okay. If your input space has infinite cardinality, then the space of functions is going to be infinite dimensional in size. Okay. So in that sense, a non-parametric model is a model that can give basically distributions over that is dense in the space of functions. There's this infinite space of functions. So dense in the sense that what we like to do is to say that as we have more and more data, we like to have some argument that our model can capture any possible function that we might be interested in. Okay. So that's kind of an example. You can think of a Gaussian process as basically it is a Bayesian nonparametric model. It's a Bayesian model, and it's nonparametric in the sense that it is actually a joint distribution, a distribution over functions that's infinite dimensional in size. Okay. Yep. Okay, let's come back to this. So does that answer your question? Okay. So I'd like to say a few words, I guess spend a few slides talking about what are the various reasons that you might want to take a Bayesian nonparametric approach. Okay. So the first reason, and actually this is the first reason that people thought about in machine learning when they first encountered Bayesian nonparametrics, is actually this issue of model selection. Okay. So whenever you have a parametric model, say, for example, you are trying to do a clustering and you're trying to do a mixture model for clustering, you have to first declare how many clusters are there in your data. Okay? If you have too many clusters and you do maximum likelihood, then you could easily overfit to your data. And if you have too little clusters, then you could easily underfit to your data. So what we like to do is to select the correct number of clusters in your data set. Okay, so you need to somehow select for a model of the right size to avoid over and underfitting. Okay. Right. So the idea here is the following. So we're going to take a Bayesian approach. Okay. So in a Bayesian approach, you never do any optimization. in the sense that you never try to find a maximum likelihood parameters. All you do is compute the posterior distribution over everything that you don't know about. Okay? So in a sense, a Bayesian inference doesn't actually do any fitting. So in a sense, it cannot really, by definition, it cannot actually overfit. Okay? And the second idea is that by using a very large Bayesian model, then or one that kind of grows with the amount of data, we will not underfit either. Okay, so by using a large model, we won't underfit, and by taking a Bayesian approach, we won't overfit. Okay, so in a sense, this idea of Bayesian nonparametrics is a possible way to kind of overcome this problem of overfitting and underfitting and trying to select for the correct model. I would like to say here that it's not a panacea. It's not going to solve all our problems in machine learning and statistics, right? Because if you specify your model incorrectly, then this can still lead to misfits and low generalization performance. It's just kind of a different way of approaching this that seems to have kind of nicer properties. Kind of, okay. Okay, so here's the picture to kind of a little cartoon picture. Okay, so let's say that this is the space of objects that we're interested in learning about. Okay, so going back to the regression example, this might be the space of functions from inputs to outputs that's continuous in some way. Okay, and this is a very large space. When we take a parametric approach, so for example, we might take a radial basis function to parameterize our function from inputs to outputs with a certain finite number of basis functions. Then what we are doing is really specify a subspace of models that's a very small part of this very large space. Okay, because we are only using a finite number of parameters, we cannot possibly cover the whole space of functions. So we are working only with a very small part of this function space. Okay, and f star here is the kind of the true function in a sense that's out there in the world that we want to learn about. Okay, and typically we don't expect that our small little space will contain this true function. So the true function will be outside of this space. Okay, so all we could do is really to find the point in this space that is in a sense closest to our true function in some way. And when we try to do something like model selection, then what we are doing is we're trying to find a model of the right size. So I guess, for example, we might have more complicated models that parameterize a larger part of this space, and hopefully we can find a function in here that's kind of a good fit to our true function, but still not overfit to our data in some way. Okay, and model selection is about finding a space, a subset of the right size. Okay, that kind of balances over and underfitting. Of course, when I draw a diagram like this, the thing that you should be thinking about is why are we limiting ourselves to this small part of the space? Okay, so if this is the space that we're interested in learning about, maybe what we should do is to actually come up with a model that actually can operate over this whole space. Okay, so what we'd like to do is to have a non-parametric model that gives possibility of learning about any possible function in this space. Okay. But of course, because this is such a complicated and large space, what we often need to do is to make certain modeling assumptions. Okay, and what that basically boils down to is that even though we would like to learn about this whole space of functions, we still would like to give some prior which says that certain functions, simpler functions, are still preferred over more complicated functions. Okay, and that's what I guess the grayscale is trying to indicate here, which is that there are certain functions in here that's simpler, and then certain functions which are more complicated, and we would like to have a model that gives mass over the whole space, but higher mass to the simpler functions. That kind of expresses both our prior knowledge, both about the fact that we like to learn about this whole space of functions, and also that there are some functions which are simpler and some which are more complicated. Okay, Yep, so I guess I've talked about this already, and I've talked about regression. So another example is density estimation, right? So in density estimation, instead of inputs and outputs, we only have inputs, and we have a certain collection of data points here. And what we'd like to learn about is basically density over this input space. So we like to learn that there are certain parts of the input space that have higher density, so it has higher probability of containing more data points. Okay, so we like to learn about a density over our space, and a density you can think of as a function as well. Okay, it's a positive function, and that typically we like to assume to be continuous, and of course it has to be a function with certain properties. In particular, that the integral of this function has to be 1 for it to be a density. Okay, so that's a kind of a second reason for why you would like to do Bayesian nonparametrics. A third reason that people have been exploring Bayesian nonparametrics is that there are often problems where we like to learn about certain structures, discrete structures about from our data. Okay, so for example, you might want to learn about basically hierarchical clustering, or in genetics, you might want to, in phylogenetics, you might want to learn about the evolutionary tree that leads to a certain collection of organisms. Okay, so those trees, of course, are going to be some discrete structures that we like to learn about. In graphical model structure learning, we might want to learn about the structure of graphical models that is used to explain our data. Okay, yeah, and so basically, with these discrete structures, we can often think of this as kind of combinatorial structures. And so if we take a Bayesian approach to learning about structures, then what we need to do is to give priors over combinatorial structures. And a lot of Bayesian nonparametric models basically give us priors over these combinatorial structures that have properties that are reasonable and sensible. Yep, and actually, interestingly, nonparametric priors often end up actually leading to learning algorithms that are often simpler than the corresponding parametric approaches. And the reason is that for that is that basically when you take a parametric approach, then you have to worry a lot about model selection. You want to know about the number of latent variables in your model, in your graphical model, the way the latent variables are connected to other latent variables or to your observed variables. And that's when you take a parametric approach, that problem of structured learning boils down into a problem of model selection, and model selection can be very difficult when you have this when you are trying to select for a very complicated model over a very complicated space. And often nonparametric approach actually leads to simpler algorithms. Okay. A fourth reason that various people have thinking about when they work with Bayesian nonparametric models is that there's many interesting properties of these Bayesian nonparametric models that is often very, very useful. Okay, particularly, there are two things which I'd like to highlight. The first one is this idea of exchangeability, which will be one of the threads that kind of will go through that will return to time and time again over my lectures. So this is an idea that if you have a data set of n data items, you don't typically believe that the way you order the data items should have any influence on the inference that you can get from your data set. Okay, so that is an assumption of exchangeability. You can kind of basically permute your data set without affecting what you learn about the data. Okay. So another property that's very useful that Bayesian nonparametric models have, and which actually many parametric models don't have, is actually power law behaviors, which we know is often observed in various natural phenomena. Okay, so we often observe power laws in linguistic data, in earthquakes, in networks, and so forth. Okay, and a lot of Bayesian nonparametric models allow us to model these power laws in a very nice way. There are returning to this problem of building complex models from simpler parts, the idea of Bayesian nonparametrics allows us to gives us different ways of building more complicated models. Okay, so before I end this motivational section, I'd like to end with are nonparametric models nonparametric? Okay, so it's not really that they are nonparametric. It just means that they are not parametric models. Okay, so cannot be described by a fixed finite set of parameters. Okay, they still have parameters. It's not that they don't have parameters. A second point to make is that there's no free lunch. Okay, so you cannot really learn from your data unless you make assumptions about your data. Okay. Of course, non-parametric models still make modeling assumptions. They are just less restrictive than typical parametric models. Okay. One thing I like about the Bayesian approach to learning is that we are taking a Bayesian approach often forces you to be honest about basically all the assumptions that you make about your data and about your learning process. Okay. Yep. Okay. So, and finally, models can be non-parametric in one sense and parametric in another sense. And typically, actually, these are the models that we work with often have this flavor. Okay. So there might be some aspect about our problem that we like to make a non-parametric, and certain other aspects that we like to kind of make certain simplifying parametric assumptions. And you can call this not really non-parametric models, but maybe semi-parametric models. Okay. Are there any questions? Okay. So this is just kind of some high-level motivations for, I guess, why I'm interested in Bayesian nonparametrics. Yes.
So what are the disadvantages then?
Well, computations is more complicated, I think. But that's, I think, generally true of Bayesian methods. You kind of often need to work harder because of this separation between modeling and algorithmic, the models and the algorithms. You often think about the models first without thinking about the algorithms, and then when you think about the algorithms, you realize that, oh, maybe actually it might be too complicated, and you have to start making approximations. So I think in that sense, it forces you to think a bit more clearly, but it also forces you to, because it's keeping them separate, you may end up running into trouble algorithmically. You know, you may end up with inference algorithms that are less efficient. Okay. Yep. Okay. So there are going to be 3 parts to this series of lectures. There could be 3 lectures. So the first one, actually, this lecture is going to be mostly about the Dirichlet process because it's actually a cornerstone of Bayesian nonparametrics. So I'd like to spend some time talking about what it is. And then the next 2 lectures is going to be trying to go beyond the Dirichlet process. Okay. And there are a certain number of key concepts that I'd like to kind of highlight here. I've talked about exchangeability already. I've talked about power loss. Another key concept is the idea of a stochastic process. Basically, all of this distributions over infinite dimensional objects and over functions, those are all basically stochastic processes. Basically, you can think of a stochastic process as a model over a infinite collection of random variables. And I think that one of the things that I think people have changed the way people think about modeling problems in Bayesian nonparametrics is that these stochastic processes are themselves, you can think of them as basically first-class objects in a probabilistic modeling language. Okay, so the idea is that anything that you can do with random variables in graphical models, in graphical models, you can replace your random variables, which are typically simple random variables, with stochastic processes. Okay. Okay, I'll come to the rest later. Okay, so I'll start with the Dirichlet process. As I said, this is a cornerstone of modern Bayesian nonparametrics. And it's such a simple process that has been discovered and rediscovered many, many times throughout history or throughout the past 50 years. And particularly, it's been discovered many times as the infinite limit of finite mixture models. And that's how actually people in machine learning started thinking about Bayesian nonparametrics, is through finite mixture models and trying to take the infinite limit of it. It was formally defined by Ferguson 40 years ago now as a distribution over probability measures, which we'll see later. And there's lots of different ways in which we could think about Dirichlet processes. Okay, so and particularly we'll look at 3 different ways of thinking about them. The first one is this infinite limit of a finite mixture model. The second way is what's called a Chinese restaurant process, and the third way is called a stick-breaking construction, and we'll see all 3 later today. Okay, I'll start off with clustering. So, okay. So I guess I've shown this slide before. So what we'd like to do is to do clustering. So in other words, we'd like to take our data set and cluster it into different homogeneous populations. And the way we're going to approach this is going to be a model-based approach to clustering. Okay, and basically this is the mixture modeling approach. So what we're going to assume is that for every observation xi, we're going to model it as saying that it could come from one of the clusters or populations that we don't know yet, that we don't know about, that we'd like to learn about. Okay? And zi basically is a latent variable which describes which cluster xi belongs to. And theta star k is going to be the parameter of cluster k. And we're going to place a Dirichlet prior over our mixing proportions and over the parameters of our cluster. Okay, and a prior over the parameters of our cluster given by h. Okay. So what is the Dirichlet distribution? It's basically a distribution over this k-dimensional probability simplex. Okay, so basically over the collection of vectors pi of length k, such that each element of pi is going to be non-negative, and they have to sum to 1. Okay, and it's given by the following density. So basically, the probability of a probability vector pi. Okay, so the density of a probability vector pi is going to be given by this form. Okay, yep. Where this part here is the normalization constant, okay, where gamma is this gamma function, okay. Yeah, and this bit here is the bit that actually depends on pi, okay. Have you guys seen Dirichlet distributions these 2 weeks? Yes, okay, so I can go through this quickly. And this is a standard distribution on probability vectors due to this conjugacy to multinomial, okay, to the multinomial. So I'd like to show a slide to just give you some idea for what a Dirichlet distribution looks like. So it's parameterized by a vector as well of a positive vector. Okay. If this vector here is all 1s, what that gives us is a uniform distribution over our probability simplex. Okay. So in this case here, we're looking at vectors of length 3, so that basically we're thinking of this as basically a mixture model with 3 clusters. Okay. The corners of this triangle here correspond to basically a probability vectors that give probability 1 to one of the clusters and probability 0 to the other 2 clusters. And any point in between is basically, so for example, this point here would say give probability 0.8 to that cluster, 0.2 to that cluster, and 0 to that cluster, for example. And then the point right in the middle is going to be 1/3, 1/3, 1/3 for each of the clusters. Okay. So when the parameters are 1, 1, 1, we get a uniform distribution over this probability simplex. When the parameters are greater than 1, what we get is actually a unimodal distribution over our probability simplex. So the color here basically corresponds to the density of our Dirichlet distribution. Interestingly, when the parameter is less than 1, but it has to be greater than 0, then instead of a unimodal distribution, we get a multimodal distribution where the modes actually fall onto the corners of the probability simplex. Okay. Okay. So we're taking a model-based clustering approach to clustering, right? So here's our model now, and what we'd like to do is, given observations of the axis, we'd like to learn about z, pi, and theta. Okay, And of course, these are all unknowns. So what I'd like to do is to infer this. And one approach to doing inference is Markov chain Monte Carlo sampling, in which basically we're constructing a Markov chain such that at convergence, as you run the Markov chain for long enough, we actually get samples from the posterior distribution of all the unobserved variables. Okay. Have you guys learned about MCMC sampling? No? Okay. Yes, no? Not, okay. So it looks like not really. Okay. So, so the idea of MCMC sampling, particularly there's an approach of MCMC sampling called Gibbs sampling, is that there are three things that we don't know about, and we're going to try to learn about these three things in an iterative manner in the following way. Okay, so let's suppose that we know what the parameters are. Okay, so if we know what the parameters are, then we'll know then we can compute the conditional distribution of Zi given the parameters and given our data. Okay, so we can compute that conditional distribution, and typically it turns out to be kind of relatively simple. So you can compute the conditional distribution, and then what we could do is we could draw a sample from that conditional distribution. And the hope is that when you draw such a sample, then it should give high probability to values of this variable that are more likely given the current setting of the parameters and given your data. Okay, so that's one step of Gibbs sampling. So where we can assume that we know what the parameters are and we'd like to learn about the latent variables. Now, and the second step, after we have sampled what the latent variables are, we will also like to go back and say, what can we learn about the parameters? Because we don't know the parameters to begin with either. Okay, so what we could do is to say, conditioned on the latent variables and conditioned on our data, what is the conditional distribution of our parameters? And in this case, it turns out that the conditional distribution of the parameters is also going to be simple, and you can calculate them, and then you could sample from a new value for the parameters, given the data and the current value of the latent variables. So now we have kind of completed one step of our MCMC update, okay, where we have updated the latent variables, we've updated the parameters, and we just repeat this procedure over and over again. It's a bit like a stochastic version of the EM algorithm. Okay, in the EM algorithm, we don't know latent variables, we don't know parameters, and we iteratively learn about one given the other. Okay, and Gibbs sampling has a similar flavor. Okay, right. So for this particular model, you can calculate the conditional distribution of the latent variables given the parameters and our data, and that turns out to be simple, turns out to be Dirichlet distributed. You can also compute the conditional distribution of the parameters given the latent variables, and that turns out to be simple as well. I'm sorry, I got a little bit confused. Condition on the parameters, the latent variables basically correspond to, for each data item, which cluster it belongs to. And the probability of it belonging to cluster K is simply going to be the prior probability of it belonging to cluster K times the likelihood, which is basically the probability of the observation I given the parameter of cluster K. Okay, so that bit we can compute easily. Conditioned on the latent variables, then the parameters, the conditional distribution of the parameters are also simple. The conditional distribution of pi is going to be Dirichlet. Okay, and the conditional distribution of the thetas is going to be the prior times the likelihood again. Okay. So both of these steps you can easily do. Okay. So we are sampling the parameters given the, sampling the latent variables given the parameters, sampling the parameters given the latent variables, and we just iterate this until convergence. And at convergence, you can show that this sequence of parameters and latent variables will converge to the posterior distribution. Okay. Turns out that actually this Gibbs sampling approach is not as efficient as another approach there's also a MCMC sampling algorithm called collapsed Gibbs sampling. In collapsed Gibbs sampling, the idea is that we're first going to marginalize out the parameters of our model, okay, which, if we assume that our prior over our cluster parameters is conjugate to the likelihood, then it turns out to be tractable. You could actually calculate that. Okay, so you could first marginalize out the parameters of our model, and then all we end up with that we don't know about is the latent variables which describe the cluster that each data item belongs to. Okay, and now we can do Gibbs sampling in this reduced space where we only operate with the latent variables Zi. Okay. And the way we're going to update the latent variables is again using Gibbs sampling. So we're going to calculate the conditional distribution of Zi equaling cluster K, given all the other Zi's and given all the observations and with all the parameters marginalized out. Okay, and if you actually go through the math, what you end up with is that the conditional distribution of Zi equals to K is going to be proportional to, again, a prior term times a likelihood term. Yes?
I've seen that in literature, people usually have this prior term alpha over K, or just alpha.
Just alpha, yep. Okay. So this is actually, the difference is the following. So, well, it's actually not really very different in the finite mixture model case. In fact, you can just redefine alpha as alpha divided by K, and then everything's exactly the same. The difference is that as you try to vary K, if you actually parameterize your Dirichlet with alpha, with a vector of alphas, then as you change K, that actually changes the prior distribution over the way the data items are clustered in a very significant way. Okay.
But the parameterization in that sense wouldn't be identical because in the denominator you would still have alpha.
So if you reparameterize it, this is going to turn into alpha, and that's going to turn into K times alpha.
Yeah, but
yes.
People usually, what I've seen is people in both numerator and denominator have the same alpha.
It wouldn't be the same alpha typically. It's typically in the denominator it would be K times the alpha in the numerator. Yes, yes. And the reason why I'm dividing this by K is that basically the parameters of the Dirichlet have to do with basically the strength of the prior, and in fact the sum of all the alphas in the Dirichlet corresponds to the strength of your prior. And so what happens is that if you try to vary K, then you're actually changing the strength of your prior in a significant manner. By dividing the alpha by K, the sum is always going to be alpha, no matter what K is, so that you can kind of like separately parameterize the number of clusters and the strength of your prior in an independent manner. Okay. Right, so the conditional distribution of Zi given the other Zi's is going to be, as I said, proportional to a prior term times the likelihood term. Okay, the prior term is very interpretable. It's basically going to be, this is a fraction, so the denominator actually doesn't depend on K at all, so we can just ignore. In the numerator, nk minus I is actually simply the number of other data items that are currently assigned to cluster K, besides the current data item that we're interested in. Okay, so basically, if all the other data items if lots of the other data items are assigned to cluster K, then we expect a priori that this current data item should have a higher probability of being assigned to that cluster as well. It's a bit like following the crowd, right? So if lots of people want to belonging to a particular cluster, then you expect that you kind of would like to belong to that larger cluster as well. Okay. Alpha over K is basically a pseudo counts parameter, okay, which basically comes from the prior, and the idea here is that even if nobody else belongs to a cluster, there's still going to be some probability that you belong to this cluster. Okay. This is a likelihood term, which is basically the conditional probability of our observation given conditioned on all the observations that are currently assigned to that cluster K. And you can calculate that. Is this a conditional distribution? Is this a prior times, yeah, it's basically that, okay? Right, so that's a Gibbs sampling. That's the collapsed Gibbs sampling algorithm for this finite mixture model. Okay, and now, so the idea is now we are going to take K to go to infinity. Okay, so the idea is that in a finite mixture model, we are assuming that there's a finite collection of populations that generates our data, but typically we cannot actually. Typically, we believe that our data, that actually out there in the world, there's kind of lots of populations that we may or may not observe in our data sets, right? So there's possibly, in effect, and possibly an infinite number of clusters. Okay, so what we'd like to do is to take K to go to infinity in some way. So before we take K to go to infinity, let's just imagine a very large number of clusters. Okay, so we're going to just imagine a very large value of K. Okay, so what we can assume now is K is very large, but N, which is the size of our data set, is going to be finite. We're going to fix N because that's simply the number of observations that we have. So at some point, K is going to be larger than N. So there are at most N occupied clusters. So actually, most of the components will actually be empty. Most of the mixture components wouldn't actually have any data associated with them. Okay? And so we can lump these empty components together and say that we can write the conditional probability of Zi equal to K for the components which have some observation associated with them. And then we can write down the conditional probability of Zi equaling some K, which is an empty cluster. Okay? And we can just lump them together. And we're going to get two terms here. The first one is simply, as before, that's going to be proportional to the number of data items, other data items that are currently belonging to that cluster K plus alpha over K times the conditional likelihood. And then this term here is going to be alpha divided by K times the number of clusters that are empty. Okay, so K star here is the number of non-empty clusters. K is the total number of clusters, so K minus K star is the total number of non-empty clusters. Okay, so we sum those up, we're going to get this term here. Okay, so now notice that we can now take K to go to infinity because as K goes to infinity, all that happens is that this term goes to 0, okay, and that term goes to 1. Okay, so we're just going to be left with the following in a sense simplified algorithm. Okay. Where the conditional probability of Zi equals to K is simply going to be proportional to the current number of data items other than I that belongs to cluster K times the conditional likelihood. And the probability of it belonging to some new cluster is going to be proportional to alpha, our parameter, times the conditional likelihood. Okay. So this is kind of quite a simple model, quite a simple algorithm, and you can actually run this. Okay, so it's intuitively the algorithm just kind of operates in a way where you can always introduce new clusters, because whenever you calculate this conditional probabilities and you sample from this conditional, then if Zi belongs to a new cluster, empty cluster, what that says is that you're going to introduce a new cluster into your algorithm, okay, into your model basically, okay, and that's the probability of introducing a new cluster. Yes.
So I understand that here alpha likely determines the number of clusters in the model.
Mm-hmm.
So if alpha is too large or too small,
Yes.
it's possible to overfit or
Yes. So it's not. I won't think of it as overfitting or underfitting. Rather, it's more like misfitting, I think. Because when you think about over or underfitting, that really has to do with problems of model selection. And here, you're not really doing model selection. You only have one single model, right? But it's true that if alpha is too large, then you might end up with more clusters than you expect to, than you like. And if alpha is too small, then you could have less number of clusters. It's true. So typically so actually, maybe I should come back to this. So the intuition here is that if alpha is large, then the conditional probability of introducing a new cluster is going to be larger as well, because we're going to be alpha times this conditional likelihood, right? So if alpha is large, then this probability is going to be large as well. Okay. And if alpha is small, then this probability is going to be small. So alpha, in a sense, controls the probability of introducing new clusters, and in effect controls the posterior distribution over the number of clusters that kind of is used to explain the data. Okay. So the difference between this approach and a model selection approach, where you fix k and you try to actually select the correct number of k, is that when you try to select the k, it's kind of like a discrete optimization problem. You're trying to find a k, but k is an integer value, and it's typically much harder to optimize an integer value hyperparameter, so to speak. Okay, while over here, alpha here is simply a positive real valued parameter, and it's much easier to optimize over a real valued parameter. So in a sense, it's kind of easier to work with. And typically what we do, and what I'll recommend people doing, is actually to place a hyperprior on alpha as well, and actually learn about alpha too. In fact, yeah, alpha does affect, govern the distribution over the number of clusters in a kind of quite a strict way. So you like to kind of relax that assumption by placing a prior on alpha and learning about alpha too as part of the same learning process. Okay. So the problem with this infinite limit of collapsed Gibbs sampling algorithms is that actually, if you look at the infinite limit of the finite mixture model, it actually doesn't make sense. Okay? And it doesn't make sense because if you look at the prior probability of any of the one data item being assigned to any of the clusters in particular, as the number of clusters grows to infinity, the probability of one particular cluster being used is going to go to 0, right? So the model actually doesn't make sense because any particular cluster will get a mixing proportion of 0. Okay, and I guess people started thinking about this and have come up with kind of different ways which is able to kind of make this infinite limit construction more precise. And the first one, which we're going to talk about, is the Chinese restaurant process. And I'm running really late. Okay. And then there's a second approach which is stick breaking, and both are kind of different views of the Dirichlet process, as I've said before. Okay, so I'll start off with the Chinese restaurant process because I would like to at least end with this by the end of this lecture. Okay. So I think I mentioned earlier on that when we the objects that we're interested in learning about, often we can think of the natural space of objects that we're interested in learning about. Okay? In the case of clustering, well, what I would like to argue is that this natural space of objects is the space of partitions. Okay? So what is a partition? A partition is basically, let's say that we have a set S, so we have a set of data items. Okay? A partition of a set is simply defined in the following way. Mathematically, it's going to be a disjoint collection of non-empty subsets of S whose union is S. Okay? So for example, if our collection of objects is these 6 people, then here is a partition where we've put Alice and David into one cluster, Bob, Charles, and Emma into another cluster, and Florence into another cluster. All of these clusters has to be non-empty, okay? And they have to be disjoint, and everybody has to belong to one of the clusters. So their union has to be the whole set. Okay? Given a finite S, a finite set S, then the number of partitions is going to be finite as well. It's going to be very large, super exponential number of partitions, but it's going to be finite nevertheless. So we can denote the set of all partitions as script P of S. Okay? And so what I like to argue is that this space of partitions, script P of S, is the natural space over which we should be thinking about clustering problems. We like to learn about partitions of our data sets. And this is the space of all possible partitions. Okay? And if we take a Bayesian approach to a clustering problem, then what we'd like to do is to, of course, define a prior over this space, and then define a likelihood of our observations given a particular member of this space, and then compute the posterior distribution. So if we have a prior over partitions, then we can define random partitions now. Basically, these are random variables that takes values in this space, PS. Okay? And in particular, we'll be working with partitions S, which is basically going to be indices 1 to n. Basically, these are going to be the indices of our n data items that we're interested in. Okay. So what are random partitions? I'll just give you one example of a random partition. Okay. And that's the Chinese restaurant process. And the metaphor, I'm just going to describe to you the metaphor. The metaphor goes as follows. Let's imagine that we have a Chinese restaurant, okay? And the Chinese restaurant has lots of tables. And customers are going to go into the restaurant one at a time. The first customer that comes in will sit at some table. Let's just call it table 1. Okay? So customer 1 sits at table 1. The second customer that comes in now has a choice to whether to sit with the first customer or at a new table. Okay? In this case, the second customer decides to choose to sit at a new table, and we can call that table 2. The third customer now has 3 choices, whether to sit with customer 1, customer 2, or a new table. Okay? In this case, 3 is going to sit with customer 1 at table 1, and then customer 4 comes in, now has 3 choices, whether to sit with at this table, or a new table. In this case, 4 sits with on the third table, a new table. And we can kind of repeat this. Okay? And at each iteration of this generative process, the customer that comes in will sit at the table C with probability proportional to the number of customers currently sitting at that table. And the probability of the customer sitting at a new table is going to be proportional to alpha, our parameter. Okay? So the idea here is that customers are sociable, and they like to sit where there's lots of customers already. Okay? And basically, customers in this Chinese restaurant process correspond to the elements of S, or our observations, and the tables correspond to clusters in our partition row. Okay? So one of the properties of this CRP process is that it has a rich gets richer property, right? So the idea is that large clusters are more likely to attract more customers. Okay? You can multiply all of these conditional probabilities together. So you take the first customer coming in, there's no choice involved, so there's no conditional probability. Second customer, you can write down the probability of sitting with the first customer or at a new table, and you can just write down all of these conditional probabilities together and multiply them all together. That's going to give you the overall probability of your partition row. Okay? And you can work out that actually this overall probability has a functional form which looks like this. Where basically this term here, actually gamma of C here is going to be a table in your restaurants, and this is size of C is actually going to be the number of customers sitting at the table at the end of this process. And gamma of the size of C is actually going to be NC minus 1 factorial. Okay? And that's going to come from the product of the terms coming from here. This ratio of gammas is going to be simply comes from the products of the denominators of this sequence of conditional probabilities. And alpha raised to the number of tables has to do with the fact that every time you introduce a customer sits at a new table, we're going to introduce a term of alpha into our conditional probability, and we're going to get that term. Okay. Yep. So and this here is basically the probability mass function of our partition, and it's called an exchangeable partition probability function. Okay. I'll come to what is meant by exchangeable a bit later. Basically, it has to do with the fact that, interestingly, so when I described this CRP, I'm describing this as an iterative process where one customer comes in at a time and then sits at some tables. Okay. It turns out that actually the distribution over partitions that it induces doesn't actually depend on the order in which customers come into the restaurants. You could have any order in which the customer comes into the restaurants. At the end of the day, the probability of the partition that it generates doesn't actually depend on the other order. It just equals to that quantity here, which only depends on the number of clusters and the sizes of the clusters. Okay. Right. So coming back to a question just now, the alpha parameter actually governs the number of clusters in our partition in a significant manner. In fact, you could show that the expected number, actually both the expectation and the variance of the number of clusters in this Chinese restaurant process grows logarithmically in n, okay, and it actually grows linearly in alpha. So the larger alpha is, the larger the number of clusters we expect to see. Okay. So here's a little diagram where basically this is the index of the customers, and here's the index of the table, and whenever a customer sits at a table, we're going to draw a point at that point. Okay. So basically we see this kind of like this is a bit like a so basically these tables are tables with more customers, and then these tables are tables with less customers. Okay. Here we have a distribution over the number of tables that's occupied by 100 customers, where alpha equals to 10, and what we see is that actually the distribution over the number of occupied tables is quite a narrow distribution. Okay. So what this is saying is that under the CRP, we expect that the number of tables in the number of clusters in a data set of size 100 has to be somewhere between 17 and 35 or something. Okay. So of course, this is quite a strict prior. So we can relax this prior by basically introducing a prior on alpha and then mixing over that. That's going to produce kind of a wider distribution over the number of clusters. Okay. Yes. So that's the Chinese restaurant process. So how do we actually construct a model for clustering using a Chinese restaurant process? It's kind of obvious what we do now, right? So given a data set S, okay, what we'd like to do is to partition it into clusters of similar items. And we're going to take a Bayesian approach in which we introduce a prior over partitions. And we're going to use a CRP for this prior. And given a partition of our data set, every data item is now going to belong to one of the clusters in this partition. And we're going to parameterize each cluster C in our partition using a parametric model. So think of this, for example, as a Gaussian, parameterized by a mean and a covariance matrix for that cluster. Okay. Yep. And I guess I didn't really complete this, but basically what happens is, for all the data items in that cluster, we're going to model it as drawn from this Gaussian. Okay. Yep. Okay, so that's our mixture model. Yep. So we have a prior CRP prior over partitions. We have a prior independent prior for the parameters of each cluster, and then for xi, we're going to model it as coming from this Gaussian parameterized by the parameter corresponding to that cluster. Okay, and that's it. Right. So this completes our model. The only thing unknown, things which are unknown here are the row, which is our partition, and the parameters of each cluster in the partition. And then if you compute the posterior distribution over this, you get kind of the, you learn about what are the likely ways in which our data set gets partitioned or clustered. Okay. So how is this related to a finite mixture model? Basically, what you could do is, given a finite mixture model, you can actually work out what is the induced distribution over partitions given by that finite mixture model. Okay. And basically, for a finite mixture model, we are given k, and what that means is that k is going to be the maximum number of clusters in our partition. Okay. And you can work out what is the actual distribution over partitions. And as you take k to go to infinity, what you could show is actually that the induced distribution over partitions is going to approach basically the Chinese restaurant process. Okay? So basically, you can think of the CRP as the distribution over partitions that we get as k goes to infinity. And in that sense, we've kind of like mathematically made sense of what's meant by this infinite limit of finite mixture models. Okay? So in summary, the Chinese restaurant process is this distribution over partitions over a collection of data items. We can use it to build non-parametric model-based clustering models. Okay. Yep. And I'll return to this idea of random partitions quite a bit over the next 2 lectures. Basically, they are generally useful concepts for structured learning problems. And we can use this to construct other combinatorial structures, things like hierarchical clusterings using fragmentations and coagulations. It's quite a nice theory there. Okay. I guess I'm running really late, but I guess I should stop now. You think? Okay. Yeah. Yep. So I guess we'll continue after lunch maybe. Yeah.
Questions?
Yes. Yep.
All right.
Can you compare the power of nonparametric methods to the regularized methods?
Regularized.
Yeah, so
parametric.
Sparse
okay.
models.
Mm-hmm.
I mean, yeah, can you briefly compare how powerful nonparametric methods are than sparse models, or vice versa?
To sparse models, as in things like lasso-based things.
Yeah.
I think there are different approaches. The nice thing with a lot of these sparse methods is that they are kind of structured in such a way that computations are very efficient in this model, so it's a lot more scalable. With Bayesian nonparametric models, the sort of problems that people try to tackle are quite different. And particularly, I think the sort of successes that people have with Bayesian nonparametric models are actually on problems for which I think the sparse models in which the sparse models don't have as nice solutions for, I think. And this, so I think the sort of problems that are successful are things like, I personally like this language modeling type of applications where we know that in linguistic type of applications, we often observe power loss, and we would like to build that into our model. Okay? When you work with sparse priors, there's no notion of power loss there, and it's quite difficult to think about how that prior knowledge can be put into your model in a way that makes sense. Okay. While for Bayesian nonparametric models, that's very natural. It actually comes out from the model. So I think, I don't know, that's kind of the thing. Yeah.
So I've asked Zubin the same question basically, but you gave me new reason to ask it again.
Okay.
So if you say it makes sense to put a hyperprior on alpha, couldn't I also just put a hyperprior on the number of clusters instead?
Yes, but actually, people have actually explored that. There's quite a bit of work in Bayesian statistics where they do place a prior on K, and then they try to infer K along with the rest of the model. The problem there is that because given k, the dimensionality of the model is actually linear in k, right? So given k, k actually parameterizes the number of parameters in the rest of the model. So as you change k, you actually change the dimensionality of the model that you're working with. So it's quite, you end up having to work with algorithms that are trans-dimensional in nature. You're kind of changing the dimensionality of your problem as you go along by changing k. And actually algorithms to work with these trans-dimensional models are quite a bit more complicated than these Bayesian nonparametric models. So that's one reason. The second reason is that actually there is a very nice theory that actually is Bayesian nonparametric in nature, and that actually encompasses both all this Dirichlet process stuff and all the finite mixture model, all the finite mixture models work. So basically there's a class of priors called Gibbs type partitions, for which there's one corner of it in which you get the Dirichlet process, and then in the other corner, you actually get the finite mixture model. So in a sense, you could actually take an approach which is kind of like, has both as sub-classes of the same class of models. So that's kind of, in a sense, very nice, I think.
So related to that question, this model where you put actually Poisson prior over the number of classes has been suggested as a way to handle the inconsistency of the posterior, where you say that the number of clusters in the posterior does not actually follow through the true number of clusters.
Yeah, so there is some result which shows that basically it's kind of negative result in that if you assume that your data comes from a finite collection of clusters, then a Bayesian nonparametric models are inconsistent in that they cannot actually, as your number of data points grow, then the number of clusters in the posterior doesn't converge to the number of clusters that is used to generate the data. So in the sense, that's a negative result. But in a different sense, actually, it's not surprising because you're assuming that your data comes from a finite number of clusters. But from the outset, a Dirichlet process or a Chinese restaurant process model, you start off by saying that actually there's an infinite number of clusters, right? So the assumptions are different, and of course, they are not, because the assumptions are different, they are not, we are not surprised that the inference you're going to get is going to be different too. So the question is, do you actually really believe that there's a finite number of clusters in your data set, in your whole world? If you really do believe that there's a finite number of clusters in the whole world, then you should use a finite mixture model, right? Because that's the assumption that corresponds to your prior. That's a prior that corresponds to your assumption. If you actually do believe that actually there's an infinite number of clusters out there in the world, then maybe you should use a prior that has an infinite number of clusters, which it would be a Chinese restaurant process prior, for example. Okay? So it's a question of whether you believe there's a finite or an infinite number of clusters in the world. Yeah.
Are there any questions in the observation lounge?
I think we can have lunch now.
Well, we actually have one more question in here.
So does that negative result mean that we shouldn't treat this as a model selection procedure then, if there's no convergence to some true latent number of clusters?
Yeah, it's true. We shouldn't think of this as model selection, really. It's really more like in model selection, once you've selected your model, then that's going to be the size of your model, whether you observe new data points or not, right? But in this model, in this Bayesian nonparametrics approach, when you observe new data points, you can always create new clusters or create new structures in the model, right? So it's not really a model selection sort of issue. Coming back to this issue of whether it's an infinite or a finite number of clusters, there's some interesting problems that people do care about, actually both biologists and linguists as well, which is this problem of species discovery, right? So think of a biologist going into an environment and collecting samples of organisms, and you collect a sequence of samples, and the first organism belongs to species 1, the second organism to a new species, the third organism actually belongs to species 1 as well, and you just repeat this. And you might be interested in the question of what's the chance that given my collection of n sample organisms, that a new organism that I collect from the environment will belong to a new species or not. So this is a problem of what's called discovery probability. You like to estimate the probability of discovering something new. Okay, so this is, and there's some interesting answers to the way you might estimate this discovery probability using Bayesian Nonparametric models, which I think I'll talk about later. But basically, there are some classical estimators for the discovery probability. So you guys may have heard about the good Turing estimator. Basically, you can think of the Bayesian nonparametric estimators as kind of like finite sample estimates. And then when you take the asymptotic limit of this, you actually get the good Turing estimator. So when you start thinking about what is the number of clusters in the world, I think the best way to think about it is like in terms of what's the chance that you might see something new that you haven't seen before. Okay, and I think that's kind of a better way of thinking about this problem.
Hello. Is there a nonparametric way for modeling the distribution of each cluster also, rather than the number of clusters?
The distribution of over the number of clusters?
Of each cluster.
Of each cluster?
Yeah.
You could do that. In fact, some people have worked on that actually. So, but the issue is how. The issue is that you might end up having a model that's a bit too flexible, right? So you have non-parametric over the number of clusters, and then for each cluster, also non-parametric. So you need to make certain assumptions about how each cluster looks like. So you need to make assumptions about things like, for example, it has to be unimodal, because if each cluster can be a multimodal distribution, then when you see a multimodal data set, is it one cluster that's multimodal or multiple clusters, each of which is unimodal? So if you allow each cluster to be a bit too flexible, then your inference is not going to be very useful, right? So you need to still make certain assumptions. So I think there are some Bayesian nonparametric approaches where you say that each cluster is unimodal, maybe a log concave distribution, and then you like to infer the number of clusters that way too.